All right, good afternoon, everyone. Thank you for joining us today on residential ventilation. This webinar will be recorded and the recording will be sent out to all attendees. If there are any issues with audio, my name is Erica DeLello. Just feel free to write me in the chat and I can help you out with that. So this series is sponsored by the Colorado Energy Office with training materials created by BuildTank. And Robbie and I have been working with the Colorado Energy Office to put on trainings just like this one. Here you can see we've got a list of our remaining Wednesday webinar series. There has been a change to pushing this functional testing webinar 1 week, so keep an eye out for a reminder email on that. And also I put out a poll just to assess who's in the room today. I'm going to go ahead and end that poll now and share the results. Got a lot of building officials in the room today. It's great. So in addition to these trainings, we've been offering tailored group trainings as well for your jurisdiction or company. And then we also have technical assistance for jurisdictions that are thinking about updating I-codes, and that goes from creating amendments to code reviews to attending meetings. It's a wide variety of what we can help you out with. So then in addition to that, we've got a code adoption toolkit that has a whole slew of information on updating codes, codes comparisons, all of these different resources, and there are also in the process of putting the recordings in the code adoption toolkit as well. So I've got a few additional resources posted for IECC 2021 now too. And then throughout the webinar, we do want to encourage questions, so please use that Q&A function, and I'll let Robbie know at the end, and then you can also raise your hand and I'll go ahead and unmute you at the end of the presentation if you want to ask Robbie directly. So today our presenter is Robbie Schwartz, and he founded BuildTank to be a practical building think tank to do research, education, and work with builders to ensure that their homes are not only complying with codes, but also perform. So with that, Robbie, I'll go ahead and stop sharing my screen.
Great. I am going to share my screen here. And everyone can see. So thank you so much, Erica. Thanks everyone for joining us today. I appreciate it. I am going to stop my video so that you can concentrate on the slides instead of watching me watch the slides myself. Today we're talking about the strategies of residential ventilation and indoor air quality. Let's get to the right screen. Okay, so we're going to be talking a little bit of review about air movement. We'll be talking about why we need to be ventilating, the differences between local or what we call spot ventilation and whole house mechanical ventilation, and then we'll be ending up with a discussion about filtration. So to begin, we have a poll question that we wanted to throw out there. It's a good question, a question that we get quite often in the field from builders, trade partners, code officials, owners of housing. All kinds of folks ask this question.
We'll get in a couple answers. I'll go ahead and stop it in 5 seconds. Okay.
Okay, so we still have some people out there, about 37% or so, that are saying yes, that we can build houses too tight. And we must have reached out to the 63% who are saying no, because the answer to the question really is no. The reality is that we're asking the wrong question. What we're trying to do is get control of airflow in our houses. And in order to get control in our houses, we need to build our houses tight there. And so we'll come back to that air control in a minute, but really in order to get that air control, we're building our houses tight. And we need to think then, what is the real question that we're asking there? And that real question is, can our houses be underventilated? And the answer to that is a resounding yes. Our houses can be underventilated. And in most cases, they are underventilated because we're not spending enough time on that question, on how do we ventilate our houses? How do we comply with what the code is asking us to do? And what the code is asking us to do now is to build our houses tight and to ventilate them correctly per the code. So this takes us to our next poll question, which is, why build tight and ventilate right? Could you launch that?
Yep. All right, I'll give it another 5 seconds. Okay.
Okay, yeah, so 68% got the answer to that, which is control and predictability. We want to build our houses tight and ventilate them right for control and predictability of airflow, but not only airflow, also moisture flow and thermal flow, energy through our houses as well. So we see this picture that was taken in 1936, and how we think back, to that time period versus a house that's built in 2020 or 2021. And you might wonder a little bit why our housing has changed so dramatically. And the real thing that has forced our housing to change is our changing expectations of our houses. So if you take comfort as a quick example, people back in 1936 living in this house were really interacting with their house in a much different way. They had to take comfort into their own hands. They had to build a fire in the wintertime, maybe burn some coal. They were willing to wear a sweater in the wintertime. Today's world, people are not willing to do much of any of those things. That we put in complex heating and cooling systems in our houses. And if there is an issue with that, people start complaining, let alone putting on a sweater in the wintertime. People literally want to be able to walk around in their underwear from room to room and floor to floor and be quote unquote comfortable. So efficiency expectations have changed pretty dramatically, and we've added thermal insulation to our houses, which really only began in the late 1960s. We want our houses to be safe and healthy, and we want the indoor air quality to be good in those houses. We want our houses to be durable. So all of these things are leading to us to build our houses as tight as we possibly can and to ventilate them correctly. We need to build them tight to gain comfort, efficiency, and safety and long-term durability, and ventilate them correctly from a durability perspective, from a safety perspective, and health and indoor air quality perspective as well. As we gain control and predictability of the airflow, the moisture flow, and the thermal flow in those houses, we have houses that will meet those core expectations of our houses, and have houses that will last and be durable over time. But when we're talking about building tight and ventilating right, we're talking about primarily the airflow portion and also the moisture portion. So we need to do a quick review. And if you were with us last week, this will be a very quick review. And that's to talk about how air flows in our houses. We need to think about air as a transport mechanism. Air is transporting heat, moisture, and pollutants around our houses, just like this freight train is transporting coal. And now we know that this freight train is taking coal from point A to point B, maybe from the mining pit to the coal plant or the power plant. And the issue with air is that we don't always know where it's going to take its load that it's transporting. Ideally, it's taking it from inside to outside our houses, or potentially from outside to inside our houses. But sometimes that load gets deposited inside of a wall assembly or a roof assembly, and that heat and moisture and pollutants, they can create repeated wetting and condensation in our buildings. So from an airflow perspective, we know that any air that moves into our house needs to move out of our house. We define our houses by this thermal envelope, the alignment between the insulation and the air barrier system all the way around our house, that creates this boundary condition that separates conditioned space from unconditioned space. And so that boundary condition traps a specific volume of air. And when a cubic foot of air enters our house, that means that a cubic foot of air has to leave our house, and vice versa. If a cubic foot of air leaves our house, then a cubic foot of air has to go into the house. And we can equate a cubic foot of air from a size perspective to try to imagine that it's about 4 basketballs equals about 1 cubic foot of air there. So a cubic foot of air enters and a cubic foot of air leaves. We need to have a hole for that air to move through, and we need some type of pressure difference across that hole for that air to move. So from a ventilation perspective, we're getting air in and out of our houses to help maintain indoor air quality, but also to help maintain a proper moisture balance within our houses. Because as we build our houses tighter and we gain that control and predictability, the moisture content of that air will naturally increase, and potentially we're trapping pollutants that we bring into our houses or we build our houses with, like all these engineered woods have lots of glue in them. They off-gas volatile organic compounds. If we don't ventilate the house properly, we're going to trap those volatile organic compounds inside our houses, and will create an unhealthy perspective inside the house for the occupants of that house. So ventilation and filtration become very important from a health and safety perspective in our houses here. We want to build tight again to create long-term durability, and it has to be married with that ventilation side. So that's why we get that mantra, build tight and ventilated right, because they're wedded together. They can't be separated there. From an indoor air quality perspective, ultimately, why is it an issue for us? Well, we know from this COVID era that we're currently living through, and hopefully coming to an end from, that we spend a significant amount of time in our houses. Before COVID, we spent about 90% of our time indoors. During the COVID era, we're spending probably even more than that. The Environmental Protection Agency is telling us that the indoor air pollutants are 2 to 5 times greater indoors than outdoors. So we're trying to figure out, how do we dilute those pollutants by bringing fresher air from outside into our houses and potentially filtering that air. And we need to also think about what we bring into our homes, not only from an air perspective, but from the furniture, from the cabinets, from the cleaners that we bring into our house. These are things that off-gas, that create that new car smell in our house, which actually is a sign of volatile organic compounds and other things that are actually not good for us there. Now, there's a doctor out there that tried to understand better how much time we actually spend indoors. He says that our average lifespan is 79 years, that 69 years of that 79 years we spend indoors, 54 years we spend at home, 26 years in bed, 4.3 years in our vehicles, and 6 years outside of that 79-year-old life that we might have there. So it's a significant amount of time to try to put it in perspective, how much time we actually spend indoors, breathing air that potentially isn't filtered, breathing air that's carrying, that's that transport mechanism for the pollutants that we might worry about from a health and safety perspective. Another way to think about why it matters is that air and the pollutants that it carries can have some severe health effects for us. It can impact our emotions. It can have physical impacts on it, cognitive impacts on us, and can impact our respiratory breathing as well. So this notion of filtration and ventilation is a real health and safety concern in our houses because we need to build them tight to meet our efficiency goals and to meet our long-term durability goals and ultimately meet our comfort expectations and other expectations that we have of our houses. But we also need to meet and ensure that we take care of the health impacts of that. So ultimately, what do we do? From this perspective, we need to think, first of all, about source control, to think about bringing non-toxic materials and products into our houses. We need to think about radon and building a tight house, and how do we ensure that radon never enters our house, that we mitigate it before it enters by getting that proper radon system below the foundation, routing a pipe up to the peak of our roof, and using stack effect or passive radon ventilation to get it out, or potentially make it an active radon system with a fan as well. Combustion safety is a huge issue because carbon monoxide is such a volatile gas that can ultimately kill us. We want to try to ensure that we're using as few atmospherically vented or non-sealed combustion appliances in our houses as possible. Nitric oxide is another issue that we need to think about, let alone smoking and other pollutants that are in our houses there. So moisture controls is another part of this. Moisture destroys our houses. It can cause mold growth. It can cause things to get wet repeatedly from condensation. And that condensation ability is really the single thing that destroys houses over time, is that repeated wetting of our structures, of our building assemblies there. So moisture control is a big part of what ventilation is trying to do, is to maintain a moisture level in the houses that is adequate for the occupants, but that won't ultimately destroy our houses over time here. Fresh air is a big thing that we want to ensure. Controlled whole house mechanical ventilation is one of those ways to introduce fresh air, and local and spot ventilation is one of those ways to ensure that we can get the pollutants that we put into that air up and out at the source at the time we're doing cooking, we're doing laundry, we're doing our business in the bathrooms. We need to get that air up and out as soon as we can while we're doing those activities. And that's what local and spot ventilation is all about. And now we have this ability, this tremendous ability to filter air that's not only flowing within our houses, but flowing from outside to inside our houses to help ventilate it. And we can get down to filtering very small particles, this PM2.5 size particle out of the air. We can actually filter viruses out of the air as well now in our homes. So ventilation and filtration are super important, again, from this health and safety perspective. Now, ventilation, again, we're trying to do it to help meet these modern expectations that we have in our houses. When we're applying building science on our houses to gain control and predictability of heat flow, moisture flow, and thermal flow in our houses, we are coupling that with ventilation to help get that control. We're building tight to help get that control. We're ultimately trying to get fresh air for the occupants to increase the indoor air quality of our houses. And we're adding filtration to that. So ventilation refers to this exchange of indoor and outdoor air. And that's ultimately what building tight and ventilating right is all about. Now, the next thing we need to talk a little bit more about is moisture control and ensuring that we have the proper moisture balance inside of our houses so that we ultimately don't get mold growth in that house. Now, mold is very common in our buildings. there's always some mold spore inside of our houses, and we need to understand what is needed for mold to grow. And one of the big things it needs is a food source, which is generally wood or paper-based products, dust, paint, wallpaper, insulation, all these things that we build our houses for are means for either mold to feed on directly, or they trap other things in the air like dust and other pollutants that mold like to eat there. Mold ultimately needs a mold spore, the food or nutrients that it feeds on. It needs a specific moisture range for it to grow, and a temperature range for it to grow there. So it's in that 32 to 120 degree temperature range, and 60 to 90% relative humidity is ultimately what it needs. So we can think about ways of controlling mold growth in our houses as well. If we can control the moisture content in that house, we can have better thermal control, air control, and we can promote drying potential in our houses over wetting potential. We can ensure that we're not going to get good mold growth in that houses there. So we need to think a bit about where we're placing vapor retarders, how we're doing vapor control mapping in our assembly, so that we can ensure that we have drying potential at least in one direction, if not both directions, which would be better yet, of these assemblies, because we know ultimately they're going to get wet. We need to let them dry. Just going back to that 1936 house there, why is that house so uncomfortable? Well, it has a lot of air moving through it, which means that it has tremendous drying potential. And if we take a little care of it, it's going to last for a long time, and meaning it's going to be durable. But when we layer on these other expectations onto that house, we change its drying potential dramatically. When we build it tighter so that less energy is flowing through it, we're able to trap more energy to keep us warm in the winter and cool in the summer times. We've changed the drying potential pretty dramatically in that house. So we need to think about those things when we build here. Now, what's interesting over time is that our notion of what the right humidity level inside of our houses has changed pretty dramatically. From a house perspective, we want that humidity to be as low as possible. The lower, the better, because moisture, again, is that thing that destroys houses over time. We know that air and vapor are one, so moisture is able to get inside of our building assemblies pretty easily as our houses leak air to the outside, or air from the outside leaks into our houses just when the wind blows, for example. We need to think about that first condensing surface, where we're going to migrate that moisture that's inside the air to become a water droplet that ultimately is going to become a problem inside of our houses. So again, control and predictability is what we're trying to get. One of those things is controlling the moisture level in our houses. Now, what's come up recently is that there's this health recommendation that we have a 40 to 60% relative humidity, because the higher the humidity inside of our houses, the larger the water droplet, and the larger the water droplet is, ultimately that water droplet will be heavy and will migrate to the floor. So if that water droplet is in the air, and that water droplet is in the air, and it's also carrying a virus, for example, then we have a means to get it out of the air. We have a healthier indoor air environment for us to breathe ultimately there. So what we've learned over this COVID period here is that air leaves our mouth at about 85 miles per hour. A micron is the size of the particle, and it gets smaller fast. That smaller, faster, drier particle moves further in a room than it did before. So tiny droplets are equally as infectious as these larger droplets in the air if we have a virus attached to that droplet, and they can travel farther and faster and longer, and they ultimately can lodge deeper into the lung here. So when we have a lower percent of relative humidity inside of our houses, the possible infection rate is actually higher there. If our relative humidity is higher in our houses, our infection rate is actually lower inside of our houses. So the new recommendation is that we keep our houses between the 40 to 60% relative humidity level to reduce the potential for infection in our houses there. And so it's this interesting thing that we have this kind of little dichotomy between what's healthy for our buildings and what's healthy for our occupants. And we're trying to find that range, that ideal range that's good for both. And that turns out to be in that 40 to 60% relative humidity range there. And the main reason we're kind of bringing this up is because ventilation impacts the relative humidity inside of our houses pretty dramatically there. When we're building tight, it also impacts the relative humidity inside of our houses pretty dramatically. Just by building tight, the relative humidity is going to increase inside of our houses there. So we want to try to gain control of that relative humidity through ventilating our houses correctly, and potentially, depending on your climate zone, introducing dehumidification as well to keep that humidity in that ideal location between 40 and 60% relative humidity. So again, from a building's perspective, dryer's better, but from an occupant perspective, that ideal range is between 40 and 60% relative humidity there. Okay, so, whoops, I went backwards. When we're thinking about ventilating our houses, we need to think a little bit about this difference between what infiltration is and what ventilation is. Because I get this question quite often. It's, people say, you're asking me to build my house as tight as I possibly can, but then you're telling me to poke a hole in it and ventilate that house. So what I say is just poke a hole in it there, because again, this is a systematic approach here, and we need the house to be tight, but we also ultimately need that hole in the house in order to ventilate the house and have control and predictability of that hole, of what's moving through that hole there. So that brings us to this notion of what's the difference between infiltration and ventilation here. So when we're talking about air leakage in our houses, we're talking about infiltration and exfiltration. And infiltration is this unintended or accidental movement of air into the building, and exfiltration is just the opposite of that. It's air going out of our building here. And the big thing is that it's unintentional, accidental movement of air. So we don't have any control or predictability of the air moving through that hole when we're talking about infiltration and exfiltration here. And we know that it's a load that we need to take into account when we're doing an HVAC design on our houses, because we need to make up for conditioned air that's flowing in and out of our houses through these air leakage holes in our houses. So building tight helps us gain control and predictability of air that's moving through holes that we associate with infiltration and exfiltration there. Now, from a ventilation perspective, ventilation is controlled and predictable air movement through holes in our building envelope there. We set that flow of air at a specific rate, meaning that we know exactly how many cubic feet of air or how many basketballs are leaving or entering the house. We set it at a specific schedule, so we know that the house will exchange the flow of air every hour or every day, or we know how often that's going to happen. And we also know that this is a separate and independent load on the house that we need to take into account when we do an HVAC design to properly size the mechanical equipment to heat and cool our houses there. What we also know is that some ventilation systems in our houses utilize infiltration and exfiltration air leakage holes in our envelope. But when we move air through those holes with a ventilation system, we have gained control and predictability of that air. We might not know exactly where it's coming from or where it's going through, but we know the specific rate and we know the specific schedule. Then there are other types of ventilation systems where we can take air from a specific source and we can filter that air and distribute it around our houses there. So there are, in essence, different types of ventilation systems that we can use to either leverage the holes in our building envelope or to introduce a specific location where air is coming in and out of our houses there. And again, ultimately from a ventilation perspective, the primary functions of ventilation are to provide fresh air for the occupants and to provide that moisture control, that background moisture control inside of our houses here. Now, why from a code perspective do we need to ventilate our houses? Ventilating our houses happens from a code perspective because the code tells us that we shall provide ventilation in our houses. We'll see in a few minutes here where that is triggered in the code. But this is the language I believe this is in the energy code. It says the building shall be provided with ventilation that complies with the requirements of the IRC and the IMC there. So what it's ultimately talking about is not only whole house controlled mechanical ventilation, but also spot or local ventilation. So we're going to start with spot and local ventilation. This is ventilation that's happening in our kitchens, our bathrooms, and our laundries primarily. The primary purpose of spot ventilation is to get moisture and pollutants that we generate inside of our houses up and out of our houses at the point in time that they're being generated there, so that we're not overloading our houses with moisture and pollutants and overloading the occupants there. So the minimum exhaust rates are defined in the mechanical section of the IRC, and it says that our kitchens need to exhaust either intermittently or continuously at 100 CFM intermittently or 25 CFM continuously. And our bath fans that we use in laundries and kitchens, laundries and bathrooms and sometimes other locations, also need to be able to push air intermittently or continuously, 50 CFM intermittently and 20 CFM continuously if we were to run it that way. It doesn't, however, go into the installation of these fans and specifically the ductwork in these fans to ensure that we're getting that flow of air that is required by the code. So you can see the pictures here and the duct installations. We are almost certain, just looking at a duct installed in these ways, that it's not going to be able to push the required amount that code is asking us to push in our houses there. Taking this down a level specifically to kitchen ventilation, we want to ensure that we're getting those pollutants that we're generating when we cook up and out of our houses. You can see all of these chemicals and compounds that we're creating here. Now we can move away from gas cooking to electric resistant cookings, and we can reduce a lot of the pollutants, but we still get these ultra fine particles that are produced just from the cooking process there. These ultra fine particles are sometimes formaldehydes, these PM 2.5 size particles. There's other particles as well. So there is a move to induction cooktops, and induction cooktops is a specific means of electric cooking that reduces the pollutants even more from the act of cooking itself there. We also are spending more and more time looking at kitchen exhaust hoods and their ability to actually move air from inside to outside and not just any air, that air coming directly off of the cooktops. So we're starting to see that there's a new way of rating the kitchen hood, which is called the capture efficiency, which is trying to get us a consistent standard for how high off the cooktop that hood needs to be, and also how much the hood covers that cooktop, and its ability to actually ventilate or move air up and out of the house at the time of cooking. So there's some interesting things that are happening from a kitchen exhaust hood perspective there. Okay, so this takes us to our next poll question. This poll question asks, can you install a recirculating cooking hood, ventilation hood, in our houses, in our new IECC 2021 houses?
We'll give it another 5 seconds.
Okay.
Okay. You look pretty even here.
Okay, so almost a 50-50 split, just slightly more that say yes than no. I probably should have put maybe, or it depends as well, on the answer sheet there. But what we know is that the mechanical code says that everything needs to be discharged to the outdoors. It says ducts serving domestic cooking exhaust equipment shall not terminate in an attic or crawl space or areas inside the building. However, there is this exception. It says where installed in accordance with manufactured instructions, that basically you don't need to do that. This is the large loophole. In essence, everything that is exhausting air is supposed to be exhausted directly to the outdoors, which would imply that you can't recirculate the air inside a house over a cooktop. However, this exception provides a loophole because obviously the installation instructions for a recirculating hood tells you you don't need to put in a duct from the inside to the outside for that installation here. However, there is another section of code that I didn't include in the presentation that says that the most restrictive portion of code shall govern when there is a conflict in the code. So from my perspective, I believe that kitchen hoods that recirculate should not be allowed to be installed into a house, but ultimately that is a question that jurisdictions need to address and think about out there as well. What we know is outdoor discharge, that air removed by every mechanical exhaust system shall discharge to the outdoors is listed in the code and shall not exhaust into sections that are either buffer spaces or directly inside the conditioned envelope. Exhaust openings are also defined in the house. That this 3-foot, 10-foot rule that some people know about is something that we want to ensure primarily so that we get that exhaust air up and out of the house, and we ensure that it's not next to an opening that might bring air back into the home from a ventilation perspective there. We also know that the code says independent exhaust systems need to convey that moisture to the outdoors. So these are talking primarily about dryers and other things like that, and that it deals with the installation of the ducting for exhaust systems as well as the ducting for HVAC systems that are delivering and returning air to a furnace cabinet, for example. These exhaust systems, the joints shall be sealed and they shall be mechanically fastened. So duct tape is generally not what we like to see. The foil tapes are a little bit better, but mastic is the best sealing mechanism so that when moist, warm air is flowing through this duct from the inside to the outside, it's not leaking out into our building assemblies or into attics and creating condensation on the roof deck. We also need to think about how we mechanically fasten the duct to the fan. You can see here that the screw is actually going to impinge the damper inside of that fan as well there. So often times it's really the duct installation that is impacting the ability of the fan to do its job there. And if we don't install these fans correctly, we're going to get problems in our houses like molds, mildews, repeated wetting, condensation inside of our houses there. From a whole house control mechanical ventilation perspective, we're not building leaky homes anymore because we're dealing with efficiency, we're dealing with comfort, we're dealing with long-term durability of our houses there. We need to build them tight. So we need to ventilate them with whole house controlled mechanical ventilation. And the code has a trigger there. You know, how tight does the house need to be before we introduce ventilation into that house? And basically it says that if our house is at 5 air changes or tighter, then we need to provide whole house mechanical ventilation to the house in accordance with section in the mechanical code at 1505.4 there. So mechanical ventilation is looked at in the IRC and the IECC. The top section is the IECC, the bottom section is the IRC here. As system design is telling us that we can use a supply side, an exhaust side, or a balanced ventilation system in our houses, that we need to be able to control and have manual override of those systems there. What it should also say is that we should be required to educate the occupant about these systems and why they shouldn't turn them off, but it doesn't go that far, unfortunately. And it also says that we can run, or we have to run these systems continuously, although there is an exception that where you're permitted to run them intermittently if you increase the flow rate. So for example, if my continuous flow rate was 100 CFM running 100% of the time, and I decided to run it 50% of the time, then I would need to increase the flow rate to 200 CFM of air in that case there. Now, just a quick review of the ventilation strategies. We're allowed to positively ventilate our houses. We're allowed to negatively ventilate it. That's the supply side and the exhaust side ventilation. We're allowed to have equal pressure systems or balanced ventilation systems. Now, the ventilation rate is using the ASHRAE 62.2 ventilation rate in code. It says that you can determine your ventilation rate using this table. So in this case, I have a 4 or 5 bedroom house that's 1,500 square feet to 3,000 square feet. I need to continuously ventilate the house at 75 CFM of air, 75 cubic feet of air flowing through that house continuously. The code also says that I can use this formula, and we're finding that most folks are using the formula because it's a bit more accurate. And we also want to ensure that we're not over ventilating our houses as well there. So if I have the smaller house in this equation here, still 4 bedrooms here, it's telling me that I need to use 52 CFM of air rather than the 75 CFM of air that the table is telling us to use here. So once we know our ventilation rate, we know that we can use supply, exhaust, or balanced ventilation systems. We need to decide which ventilation system we're going to use in our houses. And it turns out that the ventilation system is really climate specific, and that we need to choose the right one for our particular climate. So supply ventilation system is a system that pressurizes our houses. We're taking air from the outside to the inside of our house there. It can be a dedicated supply fan. It can be installed in the mechanical space, or it can be run through our mechanical system in the houses. What we know is that it's creating a positive pressure inside of our houses here. So from a climate perspective, we need to think about where do we have more moisture inside of our houses in relationship to outside our houses. So a supply ventilation system that's pressurizing our houses, it means that air is potentially being pushed from inside of our house to outside of our house through holes in our building envelope there. Now, we might reduce the possibility of backdrafting atmospherically vented appliances in our houses, but we need to think about where the moisture load is. Am I pushing more moisture through those holes in the building envelope? And so this strategy is often used in moist, humid climates like the Southeast in the United States, for example, because the moisture level is higher outside the house than it is inside the house, because we often do dehumidification inside the house. We do other things to control the moisture level inside the house for the occupants and for the structure. So if I'm going to use a supply side ventilation strategy, I know that I'm pushing less moist air through those building holes than if I was using an exhaust ventilation system that would bring in air from the outside to the inside. But I'm still getting control and predictability because I know the air that's moving through it there, I know the rate at it, and I know the runtime there. And because this is a cost-effective strategy, we're seeing this strategy used a lot in those high moisture areas of the United States here. Now, supply side ventilation in Colorado is used as well sometimes. This is how you often see it in Colorado, where you have a duct from the outside to the return side of the furnace, and you're actually using the furnace fan blower to bring air into the house when it's hooked up to a control that looks like this, that's down at the furnace cabinet. You can also use inline supply fans that would be connected to that ductwork there. And you could bring in air from the outside to the return side of the furnace as well that way. And so these are other ways that supply side ventilation is being used. In this case, we have a duct from the outside to the return side of the furnace here. And so air is coming from outside and just looping into the return and back to the furnace and then delivered to the house. Now, the problem that we'll see about this system is where it's taking the air from. In this case, it's taking it from the roof deck. Hopefully it's not an asphalt composite shingle that's creating a lot of pollutant and off-gassing there that you might be bringing into the house. Here's an inline fan that's bringing air from inside to outside the house here. Okay, so to our next poll question. Does the IECC require mechanical ventilation to be tested? Before we go on to the other two ventilation styles or frameworks that we are allowed to use, we wanted to answer this question and potentially show you, regardless of the answer to the question, how can you potentially test the flow of air so you can really gain that control and predictability. So it looks like we have most 73% of people are saying yes, it is a requirement. And that's true now in the 2021 IECC. It is a requirement that you actually test the ventilation and that it's proved that you're proving that it's meeting that minimum 50 CFM or 100 CFM for kitchen hoods per ASHRAE 62.2 and per the requirements that are listed in the IRC there as well. There is an exception for kitchen hoods, but I'll let you guys look at that later. When you're talking about supply side ventilation, it's not easy to measure. We're hopeful that more and more folks that are using supply side ventilation might put in a damper like this. This is called an iris damper. This iris damper has the ability to put a pressure gauge on it and measure the flow of air through the damper. And it also gives you the ability to change the opening size here so that you can change the flow rate through the damper. And in conjunction with an inline fan or in conjunction with a furnace fan blower that's bringing air into the house, this type of system can do a great job in quantifying the airflow through the system there. So there are other ways. Sometimes those inline fans have pressure ports on them that you can do measurements in. And there's some other ways to measure as well. But I just wanted to give you an idea of the importance of measuring that flow here. Moving on to exhaust ventilation systems. Exhaust ventilation systems use a single point fan, usually sometimes a multi-point fan to exhaust air up and out of the house there. Again, it creates a negative pressure inside of the house. Therefore, you're bringing air from the outside through the building envelope to the inside of the house there. And therefore, it's used primarily in drier climates because it's drier outside than it is inside in a drier climate. And so you want to bring the drier air into the house there. So again, from a climate perspective, exhaust ventilation is generally used in drier climates and supply ventilation generally used in moist climates. Again, we're able to get that control and predictability because we put that air, we're using a fan to know the rate of the air moving out in cubic feet per minute. And we've got it at some type of runtime, either continuously or periodically, but we know exactly how often it's run there. Exhaust systems can be set up with a known opening to the outside, so you can reduce the potential of air coming through random holes in the building envelope. So if you have a fan and it's exhausting air to the outside, then air is going to come back in at the same rate. Air in, air out equals air in. And if you put a known opening to the outside, air is going to take the path of least resistance. Another style of ventilation that kind of is a hybrid approach between supply and exhaust ventilation is a system that leverages the furnace cycle to heat and cool the house to bring air in on the supply side. And then when the furnace isn't running to heat and cool the house, this air cycler fan will come on using an exhaust fan there, and it will suck air out of the house there to make up the rest of the ventilation needs of the house. So you're bringing some of the ventilation air on the supply side with the furnace fan, and you're taking some of the air out and bringing it in through holes in the building envelope, potentially a known opening, but maybe not, with an exhaust ventilation system. So again, there are a variety of different approaches, either strictly supply, strictly exhaust, or a combination of the two. And when you're talking about ventilation, exhaust ventilation, this is the most often the way that you test it is you use a flow box to measure the flow going out through the exhaust fan. And then you can set these control dials on these little bit higher quality fans to set the CFM rate and the time rate to get that control and predictability of the air flowing through the fan. Now, balanced ventilation is when we get this neutral pressure in it. It's a safer system. It's bringing air in and out of our houses through a device like this, across a core where the air streams that are going in and out of our houses pass through, but the air streams don't physically touch each other, but moisture and heat can pass from one airstream to another airstream here. So it's a great way to do that. We can recover energy, so we can have these heat recovery ventilators that pulls fresh air into the home while simultaneously exhausting stale air out of the house. We're able to recover some of the heat. They're generally 70 to 85% efficient, depending on the model that you get. Again, these fresh air streams generally don't touch each other physically, but they're able to transfer heat and moisture from one airstream to another airstream. When we install these systems, you generally want to install so that we're delivering fresh air to the living spaces and we're taking stale air away from those moist areas like kitchens, bathrooms, and laundries. Now, energy recovery ventilators basically do the same thing that heat recovery ventilators do, but they're dealing with the latent load instead of the sensible load, which means that they're able to transfer moisture as well as heat in these assemblies. We used to think that that these units really only worked and should be installed in moist climate zones. It turns out that they work pretty well in drier, colder climate zones as well there. They do need to be balanced. That means that you need to test the ventilation flow rate that's going in and out of the house so that you can balance the systems. You can ensure that you have that neutral pressure there. And you can do that either by ports that are on the system and measurements there, or you can insert pitot tubes into the ducts and measure the flow rate that way as well. As we said before, you have to have control on this. You have to have the ability for these systems to be overridden by the occupants of the house there, which ultimately is a really bad idea. So one thing I like to say is the control has to be there, but it doesn't have to be an easily accessible control. And if you do put a control on, it's very important to label that control there. So those two things aren't clearly defined in the code itself, but they're important things to remember. And then the last thing with regards to control is because you have the ability for occupants to override it, you want to ask the question why they're overriding it. Most of the time they're overriding it because first, they don't understand the notion of control and predictability and why we need ventilation in our houses. And second is because they think the system is noisy. And if the system is noisy, 9 times out of 10, it's because the system hasn't been installed well. They should not be noisy systems in our houses. And I have to leave it at that because of time constraint here. I wanted to point out quickly that it's very important to locate the duct that's bringing air from the outside in locations that is bringing the freshest air into the houses there. So ensure that you're doing that. And then we're going to end today on filtration. So again, filtration is not addressed in the code itself, but filtration is very important to include in that discussion when we're talking about ventilation. So our last poll question that we're going to do quickly here is, what does MERV mean? What does it stand for? Okay, so 66% minimum efficiency rating value. And great job, that's what it stands for. So the higher the number, the more efficient the filter is there. The higher the number, the more potential resistance to airflow as well, however. So you need to, when you are designing your HVAC system, especially the duct portion of it, when you're doing your manual D, you want to take into account the need, especially that's been identified for us during the COVID era, of using a higher quality filter in it, and that you might have more static pressure drop across that filter, and therefore you want to use a better filter there. So the higher the number, the more effective it is at cleaning air here. And you can see that from a 13 to 16 MERV filter, we're starting to get at the ability of actually filtering out viruses in our system. So you're going to see more people requesting better filtration in our houses. And therefore, we need to do the design to make sure that it doesn't impact the flow of air around our houses as well. What I'm talking about is what we call a pressure drop. So we're comparing a 1-inch filter versus a 4-inch pleated filter. What we see is that a 1-inch filter has 2.7 square feet of area versus a 4-inch pleated filter has 8.5 square feet of filter area around it. The more square footage of area that we have of the filter, the less the pressure drop across that filter is there, and the better flow we have in that filter. So when you're looking at a 13 MERV filter, for example, you want to get the thickest and biggest filter that you can for your system. And same when you're designing your system, you want the thickest and biggest filter that you can get so that you have the least amount of pressure drop. Here's another way. It's saying the 1-inch pleated filter replaced at least once a quarter. Another advantage of the 4-inch pleated filter is that it can be replaced once a year. Now, I generally recommend that you replace your filter, even if it's a 4-inch pleated filter, more than once a year, because those higher quality filters are filtering more particles out of the air. They should clog faster there, but again, you have more surface area as well. So I think changing that 4-inch pleated filter once a quarter is a good recommendation rather than once a month. But you'll see some manufacturers that say that you can do it once a year there. So to conclude here, as you can see, I forgot to write the conclusions down there, but what we have learned, I believe, is that the sound building science and the mantra of building tight and ventilating right is truly embedded into the code. It allows us to do exhaust supply or balanced ventilation systems. We've learned that it's a climate-specific ventilation strategy. The one system, the balanced ventilation systems, can be used in any climate zone. But from a moisture perspective, we want to ensure that we're not using supply and exhaust ventilation in climate zones that we shouldn't be using it there. We're trying ultimately to gain that control and predictability of airflow, moisture flow, and thermal flow so that we can meet those core expectations that people have of their houses and the energy efficiency requirements that we're trying to meet in the code as well here. So thanks so much for your time today. I really appreciate it. Happy to stay on and answer any questions or have a discussion if people would like to do that. Or you can reach out directly to me through my email, phone number, or on Instagram, or take a listen to my new podcast as well. I appreciate it.
Thanks, Thanks, Robbie. I've got a lot of questions for you. So if participants can stay on, feel free. If not, the recording will be available. Just to answer your first question, if printed handouts will be available, Robbie, if you could send me a PDF of your slides, I'll go ahead and get those posted on the Google Drive for everyone. And then jumping to our questions, what is the guideline for using or controlling a duct heater with an ERV? Where should it be placed, inlet or outlet?
Well, ERV or HRV, ideally you would duct them independently of your furnace system. But if you do integrate it with with the duct system from your furnace or air conditioning system, the air that's being supplied to the house usually goes on the return side of the system so that it can get potentially extra filtration as it gets distributed. And then you're taking air out of the system, ideally not through the ducts of the system, but you would independently at least duct the exhaust air from those moist areas of the house there. There's actually a really good video series that a builder named Matt Reisinger just posted on the ERV that he installed in his own personal house in Austin, Texas, that I would recommend people look at, because it gives a good explanation of why you're taking air from certain locations and supplying it to other locations there.
Thanks, Robbie. Another question for you. What is the MPR equivalent to PM 2.5 for residential furnace filters? MPR 2200 to 2800?
MPR, I'm not sure what MPR is.
I am not quite sure either. Stanley, also feel free to raise your hand and ask Robbie any questions directly, and I can unmute you. Okay, yep, he just raised his hand. I'll go ahead and allow you to talk. You just have to unmute yourself on your end, Stanley.
Stanley, it looks like you unmuted yourself, but I still can't hear you.
Yeah,
Stanley, you're happy to email me your question or give me a call. I'm sorry, I just don't know what that acronym stands for.
Okay, we'll keep moving, but Stanley, feel free to email or chat us and we can get back to it. Do you need the same number of air exchanges on an unoccupied house versus occupied?
That's a really good question. So the ventilation rate is determined by the size of the house and the number of bedrooms in the house to give us a standardized way of sizing a ventilation system there. So the number of bedrooms is getting at the occupant load for that house. So it's the number of bedrooms plus one. And then there's a CFM rate associated to that. And then a CFM rate that's associated with the square footage, conditioned square footage of the house. The code and the ASHRAE standard do not say that if it's an unoccupied house that you don't need to ventilate it, but the reality is that you don't need to ventilate it probably at the same level that you do when it is being occupied because you don't have the other things that the occupants are doing in that house just from living it, breathing and creating moisture from taking showers and those types of things. But you would still have that house just being locked up and not being used. You would have things that you'd want to ventilate and move in and out of that house from that reason. But it could probably be at a lower rate. The code is basically silent on that and ASHRAE is as well.
Okay, thanks, Robbie. What are your thoughts on putting vapor retarder class 1 plastic basically on walls and basements covering fiberglass insulation before drywall installation? To me, you are trapping moisture from the concrete foundation wall between vapor retarder and damp proof spray. Code doesn't seem to really address this potential issue.
Well, actually code addresses it specifically. If you go to the vapor retarder section in the IRC, I believe it's 703, R703 section there, you see that it says that you have to put a class 1 vapor retarder in our climate zone, but the exception is on basement walls where you're not supposed to put that vapor retarder. So I would agree with you. Don't put a plastic vapor retarder against a concrete foundation wall in a cold climate. And I would go one step further and recommend that we don't put class 1 vapor retarders in any wall assembly or roof assembly in a cold climate, climate zones 5 and up. That there are other ways, and that section of code also gives us other means of vapor management other than class 1 vapor retarders there. But that's kind of a whole nother class, another webinar that would happen.
Okay. When using chart M1505.4.3, is the square feet of a conditioned crawl space included when calculating?
Yes. Yeah, it's all conditioned space. It's a great question because it would not only be a conditioned crawl space, but it would be a conditioned attic and a conditioned basement as well.
Perfect. How do we account for the option for natural ventilation under the code?
There is a credit that you can use to lower the ventilation rate that you calculate. I'd say it's not used very often, and I personally haven't used it. But there is an allowance there. You have to be able to quantify the air leakage rate, the natural air leakage rate through a blower door test to be able to do the calculation. But you would just have to do that calculation and then submit it when you're submitting for your building permit. And you'd have to ultimately confirm it at the end with your blower door test at the end as well.
Great, thank you. In a very tight house, how can ventilation exhaust fan, bathroom exhaust actually achieve the nameplate exhaust CFM if there is no source of makeup air?
Well, you would have to be able to build a vacuum or the space station type tightness of a house in order for air not to come back into the house. So I would say that if you are able to measure the flow rate of an exhaust fan and it is flowing at 50 CFM or greater, then you know for a fact that air is leaving the house and air is coming back into the house, because the building science tells us that air out equals air in. What you don't know is where that air is coming back in. So you might want to put in a known location for that air to come back in so that you have that known location. You might be able to filter it as well. If you measure that fan and it's not being able to push that 50 CFM minimum when it's running continuously or intermittently, then it's either because of the installation of the fan or because, like you say, the house is too tight and there aren't enough holes for that air to come back in there. So it brings up the real importance of testing our houses. And the code now asks us not only to test the air tightness of our house, but to test the ventilation fans and if they are able to meet the requirements. So if you built a house and were relying on exhaust ventilation and the house ended up being too tight, you have a choice. You can introduce a hole or you can change your ventilation strategy to a balanced ventilation strategy that would work better with a really tight house.
And get that free heat.
Yeah.
Okay, thanks, Robbie. Going back to that NPR question, equivalent to PM 2.5, NPR is micro particle performance rating, and it's the ratings on filters you can buy from Home Depot. It sounds like.
Okay. Yeah. It's a rating system that in essence competes with the MERV rating system. And I believe that there's some charts available online that try to show a conversion or how one rates with regards to the other. I am not aware of a specific scientific test that has been done to do that. I think that just individuals or manufacturers have done that work. So I'm not sure that I can answer that question or offer anything beyond that.
That's fair. I'm sure there's some resources out there that compare the two. Any reason for a barometric damper on an air inlet?
Yeah, I mean, I think there are some reasons potentially for that. You know, if you if you're worried about excessively humid air entering the house, for example, that might be a reason.
Okay. I think that's pretty much all the questions. We do have someone commenting back on the vapor retarders if you want to check that out, Robbie, in the Q&A. But otherwise, if there are any other follow-up questions, please feel free to reach out to Robbie or I, and we'll have the presentation and the PDF posted within the next few days. I did send out continuing education credits for the past several webinars. So I do have those course ID codes now. And so just keep an eye out in your inbox for those certificates. But otherwise, thank you again, Robbie, for a great presentation today. And thank you to everyone for hanging in there and staying on for a few extra minutes. So have a good one, and we'll see you next week.
Thanks, Erica. Thanks, everyone.